Some technical human difficulties here, so please just bear with me, and if somebody starts screaming, then we'll just have to live with it. So thank you for calling in today, guys. My name is Nick Colson, the IAH technical representative, and I'm here to introduce a bit about the IAH talk this month and introduce our speaker. So today we will begin with a welcome to country. So we begin by acknowledging the traditional custodians of the land on which we gather today and pay our respects to the elders past, present, and emerging. And we extend that respect to the Aboriginal and Torres Strait Islanders people here today and on those lands where we are calling in from. So if you were not aware, the IH has an Indigenous Groundwater Declaration. It's one of a kind, and I strongly recommend people jump on the website to go check it out. Thank you very much to our sponsors. You are the reason why we're able to continue to operate. We are a volunteer organization, so the sponsorship and your memberships go a very long way. We greatly appreciate it. If you haven't signed up for your membership, you can jump on the IH website and go through the membership portals. It's quite easy to renew. And then, so IH Queensland, we try to get a series of technical talks, but a good mix of industry, academia, consulting, bring hydrogeological professionals together and promote groundwater science and practices while fostering linkages between hydrogeologists and other disciplines. So should anyone want to know more or reach out with an offer for a talk, you can reach out to myself or Neil Mainwell. So upcoming talks, we actually have Neil filling a gap next month. So please dial in for that, and information will be coming out shortly. We do have a Darcy lecturer coming to Brisbane. Dr. Matt Becker will be here in November. And then in December, we will be hosting a Christmas party. I know the Queensland Social Committee or the Brisbane Social Committee is starting to work on something, and I'm hopeful that up there in other places, Townsville, Cairns, you guys will be as well. We are seeking 2025 speakers, and we need them. So please, first in, best dressed. If you want your pick of when and where in the year, please just reach out. And then also, if there's any feedback on the dates, so whether the third Thursday of each month still works well for people or the times, we'd be happy to hear that so that we can try to maximize attendance and interest. Now, I did forget to put a slide in here. There is, I think on October 9th, there is a industry mixer event here in Brisbane. So just jump on the social media and you can find out some more information. It's essentially all of the geoscience organizations in Brisbane are banding together to put on an industry student night. And if you want to stay connected, we've got a mailing list. We've got various social media, LinkedIn profiles, and early career hydrogeology network. So please feel free to connect with us on the social medias. And if there are any questions tonight, we do have a Q&A tab, so please drop some the questions in there. I will be wrangling a small child tonight, so I might not be able to get to them immediately, so we may just leave questions to the end. And without further ado, I would like to introduce the talk and our speaker tonight. So Stephen Lee started his PhD with Charles Darwin Uni in 2022 after working in consulting as a hydrogeologist. Through compiling and analyzing publicly available data sets, such as chloride and groundwater levels, he's looking to better understand how groundwater recharge varies spatially and temporally across the Australian continent. He is also looking to help facilitate better data access and sharing within the hydrogeological community. So without further ado, I'll hand it over to Stephen to present on his high-resolution map of diffuse groundwater recharge for Australia.
Thanks, Nick. Hopefully everybody can hear us here pretty well. Let me just share my screen. Can somebody confirm that you can see my shared slide?
It's coming through.
Okay. I just want to start by acknowledging our lands here in Townsville, and specifically the Wulgurukaba and Bindal people. So today, as Nick mentioned, thank you for the intro. I'm studying for my PhD at the moment, which aims to better understand hydrogeologic processes, specifically recharge in Australia. And I'll sort of run you through why and how we're doing this. And presenting this as my first piece of work for my PhD study. It is a combined effort. So I've got Monash University, Charles Darwin University, Uni of Newcastle, all working together on this. So just an overview of today's talk. I'll go through a bit about the background, my data collation process, chloride mass balance, what that is and what we do, the data filtering process. I'll talk about machine learning, which specifically we're using random forest in this case, and then talk about the recharge map that we've produced. Lastly, the limitations and the conclusions. So just a bit of background. We all probably know groundwater is stored in aquifers, and groundwater supports streams, ecosystems, and livelihoods worldwide. Just like that spring water on the side, on the left there. An aquifer is basically, you could say, it's like an overflowing bathtub. And groundwater discharges into the rivers, into springs and the ocean. But it's also pumped for human consumption and other industries as well. So you can imagine how important it is that we understand groundwater and understand each of those components there, especially recharge. Because if we use too much groundwater and there's not enough recharge, then obviously that groundwater discharge and flow will sort of cease and things will get dry. Moving on, there are a lot of challenges in quantifying recharge. So the first thing is spatial temporal variability. It varies a lot across space and time. And to think about climate as well and the amount of rain, evaporation, the type of vegetation, the soil, the geology, and geomorphology, they all play a part in controlling how much recharge gets to the water table. Another sort of aspect that is a challenge is recharge mechanisms. There's direct or diffuse recharge. There's indirect recharge and there's focused recharge. All of these are quite difficult to sort of assess. And there's also various techniques that you can use to assess and estimate recharge. For example, chloride mass balance, which is a very popular one, and water table fluctuation, which looks at using water levels. Each of these methods also have their own assumptions and uncertainties, as well as they measure different components of recharge. So for example, net recharge versus gross recharge, as you can see on the diagram there, net being after, potentially trees and plants have taken up water, and gross is basically just water's sort of gone into the ground, and that's sort of the water table fluctuation method there. While it's good practice to use multiple techniques like those two that I mentioned in assessments of recharge, as it allows us to understand how recharge has changed with time and also with climate or land cover change. Some global scale groundwater models have utilized recharge data sets that contain recharge rates that have been obtained with different techniques. And it's been shown that using different recharge estimation techniques may result in widely varying recharge rates. And these data sets add extra uncertainty to those predictive models that utilize them. So selecting a single technique is beneficial, especially on a large scale. And so just going through a few of the ideas and the approach that we've taken. Chloride mass balance is sort of the most popular method that's sort of in Australia and worldwide as well. You can see the diagram or the map on the right, that's from the Groundwater Explorer from the BOM. they've got more than 200,000 fluoride measurements just for Australia, and that can obviously be utilised, and it might be just sitting there, not really being used. Regional scale recharge mapping has been done quite a lot recently, especially by the team at CSIRO. And yeah, so they've got some new techniques or more recent techniques, which I think need to be utilized. And we've definitely utilized that in our study. And there have been older sort of studies that I think it's time that we sort of updated that with a new recharge map. And there's also been some machine learning that's been done, especially random forest in other groundwater sort of studies. But in Australia, I think this is probably one of the first studies that have utilized that. So apart from getting that fluoride and downloading that from the Groundwater Explorer and some other sources as well, we've also looked at some other different variables like geology, soils, precipitation. That's all widely available and can be downloaded as gridded raster data, basically. So that's basically what we've taken and used. So having a look at the chloride data and its sort of spatial variation across Australia, you can sort of see pretty much makes sense. You've got so just to explain the scale here, it goes from really fresh in the blue to really salty in the brown, and that's a logarithmic axis as well. And you can sort of see in the tropics, in the northern sort of regions of Australia, you've got much fresher groundwater, whereas in the southern areas and especially inland, you've got much more saline groundwater. But it does vary. There are pockets of fresh and salty water, mixed in different areas. Looking at the middle panel, you can sort of see with depth. So the y-axis goes from 0 meters below ground surface to close to 2,000 meters. And the x-axis is chloride, going from fresh on the left to salty on the right. You can see that it's rather, more saline in the more shallow sort of depths, and it does get a bit more fresher as you go deeper. And that could just be because of the geology in Australia, especially the Great Artesian Basin being a bit sort of deeper. That basin does hold a lot of fresh groundwater resources. So that's kind of interesting. And just breaking that down by depth as well, I've got on the left depths below 150 meters, in the middle 150 to 450, and then depths of more than 450 on the right. And you can sort of just make out the Great Artesian Basin on the right there. Whereas, yeah, it's a bit more of a mixture, looking at sort of the more relatively shallow depths. So how are we sort of using this fluoride data? Now, there's a handy Python tool out there called CMBear, which my supervisor Dylan Irvine and Ian Cartwright sort of came up with. It just basically is a Python code that you can just input your fluoride data into there, along with some latitudes and longitudes for your locations. And it utilizes some chloride deposition mapping, basically how much chloride is coming from rainfall, and also the amount of rainfall as well, to give us a recharge estimate. So here's just the basic equation. R is recharge, P is precipitation, CLP is chloride and precipitation, and the bottom is chloride and groundwater. Now, we've looked at basically a more sophisticated approach, and this has been developed by CSIRO, by Russell Crosby and his team. And yeah, it's a stochastic approach, which basically runs this equation multiple times to try and get a distribution of estimates. So we've modified that CMBear Python tool that basically accounts also for now runoff, and yeah, also chloride deposition, as I mentioned. The runoff term is particularly important in Australia, especially in the tropics, as the tropics are subject to large rainfall events, which can produce high amounts of runoff. And that runoff, which carries chloride away into surface water bodies, needs to be accounted for in this chloride mass balance. The runoff coefficient, which is the RC term there, is divided by rainfall. Runoff is available as a map that you can download from the Bureau. There's an alpha term that scales it basically. And it assumes that 20 to 50% of water in streams can be base flow. So 50 to 80% of water should be sourced from rainfall. And this basically is just simply reduced to a 30 to 60% sort of scaling number. Now, finally, chloride and groundwater is at the bottom. It doesn't really change. It's pretty similar. And those are just the explanations of the terms there. So the stochastic part of this, which we assume different probability distributions for all the terms except for that runoff coefficient. We use these distributions to pick a random value to go into our equation. And for each groundwater chloride point in Australia, we randomly calculate recharge 1,000 times. And I'll sort of show you what that sort of means. So first step is you get your bore where your data is, you get the latitude and the longitude. And then with this particular chloride deposition map, you extract the chloride deposition from there. So you get the mean chloride deposition, you get the standard deviation of that particular point as well, and the skewness at those same points. And then you create these distributions. So the green matches up with the chloride deposition. It's a Pearson type 3 distribution. The alpha term is a random distribution like that. And the chloride in groundwater is a normal distribution. So for example, if we randomly picked 0.2 for our runoff coefficient here, and then we randomly picked 0.5 right in the middle here for the alpha term, it will basically be 0.9. So that reduces that chloride deposition value by, not basically by 10%, reduces that. And then we run that 1,000 times to get 1,000 different values. And then we take a median value, a 5th percentile, and a 95th percentile. And you basically just press go in Python and it runs it. And you get something like this. So it's highly automatable. And you can put however many samples of chloride you want, and it will generate basically a table of those recharge results. As I said, recharge median, recharge 5th percentile, and the 95th percentile, as you can see from these three maps. So yes, we can see in this map that recharge estimates sort of make sense. They're again high in the tropical north, and along the coast, it's quite high recharge as well, just because it's close to the coast, you have high rainfall. But you'd think we could just interpolate these points and make a contour map of recharge, but this map still contains a lot of potentially erroneous values of recharge estimates that could be realistic as well as unrealistic. So what's wrong with the data? Looking at this graph here, the x-axis is precipitation in mils per year, and y-axis is recharge in mils per year. And the points are also colored by chloride concentration from purple to red. And we start to ask questions about, how can recharge be higher than rainfall, where we're looking at this dotted line where recharge is equal to precipitation, and all those points that are above it doesn't really make sense. And then we're also looking at the points down here where precipitation is relatively high. You'd sort of be in the tropics, but recharge is quite low. So you're looking at, less than 10 mils per year to 0.1 mils per year. So again, what's happening there? Is it because of seawater intrusion? You're getting chloride values that are quite high that are not to do with natural causes, or is it dry land salinity or something else like that? So that's why we applied a data filtering process, which allowed us to filter out our recharge rates where the assumptions of the chloride mass balance method may have been compromised. What's shown in these box plots that I'll show you slowly step by step are just recharge rates with a bunch of rainfall intervals, and they've been binned by 200 mil intervals. So 0 to 200 mils, 200, 400, etc. And I show some statistics on the left as well, and also the points that get removed in each step as a map on the right side. So we firstly remove bores where the screen of the bore, the midpoint, is more than 150 meters below ground surface, which it's unlikely to be in an unconfined aquifer. So yeah, you wouldn't get any direct recharge going into there. You'd have these areas that are recharge areas, maybe really far away from the point where you're sampling. We're also removing bores with chloride that are less than 2 milligrams per litre, which are unlikely to be representative of groundwater, where there could be poor bore construction, where water's just leaking through the sides and into the bore, basically too fresh. We're also removing bores where chloride is more than 2,000 milligrams per litre, and also where the water table is less than 1 metre below ground surface, as these could be in areas downstream of groundwater discharge areas, or near springs and things like that, where you wouldn't expect to have recharge, but you would have discharge instead. We then also remove bores where there are known halite deposit areas, where that would be not like a natural source of chloride from rainfall, which could be a potential additional source of chloride. So that we also removed halite zones. And lastly, where bores are within 1K of the coastline as well, to avoid situations where we have seawater intrusion. So overall, if you look at the statistics, the mean median recharge didn't really change significantly, but the standard deviation did reduce significantly. Also, some of the bores are removed in areas that are quite similar to dry land salinity areas or forecasted dry land salinity areas. So that's probably a good thing that we remove those. So after removing these, one last thing is we also removed where recharge was in excess of precipitation, which you might expect irrigation areas to be like that, or other areas where there's other sources of water put onto the land. So after filtering all those things, we were left with just over 90,000 recharge estimates. And then, we basically decided to take this one step further and created a gridded map of recharge for Australia. So how did we do that? We basically used a machine learning technique called random forest, which is an algorithm that is composed of an ensemble of decision trees. So these sort of trees on the right here, on the top right, it's a bunch of those. So there can be a whole forest of them, hundreds or 200 or 300 of them. Random forest has a classifier approach or a regression approach. Classifying basically puts things into categories, whereas regression gives you value, which is what we sort of need for recharge. There have also been many random forest applications in hydrogeology literature already. For example, assessing groundwater potential by spring locations, predicting losing or gaining streams, and identifying the origin of groundwater samples via geochemistry. And an example I'll show you is sort of down here, where they're using ionic concentrations like nitrate, calcium, magnesium to work out what aquifer it's come from. And so you can sort of see this is the building of that decision tree, starting with looking at nitrate. And it's basically trying to separate data into groups where the same sort of data or the same sort of categories will get bunched together the best way. So the algorithm basically does that. It keeps separating the data until you get these clusters of data that are most similar to each other. So you get to a point where it says, is calcium, you're taking 277 milligrams. Is it less than that? Yes, then it basically groups that together. Is it no? Then it sort of groups that together. And it's random forest is sort of like it's a best guess kind of approach, where if you have a jar of coins or something, and you want one person to guess how many coins are in that jar, they'll give you their best guess, but that guess may be really off or maybe really good. You don't know. But if you get 100 people to do the same thing, and then you take the average guess out of all those 100 people, that might give you a relatively good answer. So it sort of does this with those decision trees and builds hundreds of those to sort of give you the best answer you can get. And for our case, we're sort of trying to predict recharge. So yeah, that's sort of a similar kind of approach. And so apart from that chloride concentrations that we've got as an input into random forest, we also need a bunch of other variables that I sort of showed you before, things like precipitation, soil class, the slope of the land, elevation. And I've got 17 different variables there that have been included. Basically, you plug that into QGIS, and you can sort of sample each of those chloride points and gives you a separate column in your table with each of those variables. So what we've done with random forest is, firstly, you sort of need to train your random forest, train those trees, and you also need to separate 70% of that data set for training and leave 30% of that data for validation later on, just to check if your model's giving you sort of good answers or not. And all those 17 variables were used as input. However, when you're going and you're creating those different branches of your trees, random forest chooses a random subset of those 17 different variables at each of those breaks in the branches. So it might consider taking precipitation and soil as at one of those breaks, and it will decide which ones of those gives you the best best answer. So once we've sort of trained our random forest model, we sort of asked, are we achieving, similar performance with less variables, or should we be using as many variables as we can? So I sort of went and grouped up different variables. So we sort of grouped up the climate variables, precipitation, aridity index, evapotranspiration, all into one group, and ran some tests with those. We sort of did random forest models with geology and soils and things of that nature. And then also vegetation as well, like NDVI and vegetation class. And we found that by breaking them up into those separate groups, didn't really give us very good model results, but we ended up getting combining various different variables and getting quite a good answer. So we started off with looking at 4 variables and added one on, and continued until we didn't really see any improvements in the model. And that was at basically 8 variables: precipitation, rainfall seasonality, potential evapotranspiration, elevation, distance to coast, NDVI, which is sort of the greenness from satellite imagery, and clay percentage, and also soil class. And we basically looked at running also, different number of trees from 50, 100 all the way to 400 to seeing if that makes a difference. obviously the more trees, the more computing power you need, and the more the more runtime you'll have as well. We looked at different variable combinations, as I mentioned, and also varying hyperparameters. So things like how many branches can you have on your tree, or how many variables will you consider at each of those breaks in the tree. And this sort of just gives us an idea about how good is that performance. So I mentioned we use 70% of the data for training and then left 30% for validation. This is the 30%. And you'll see basically chloride mass balance recharge is on the x-axis, and on the left plot, you've got predicted recharge. You've got the one-to-one line in the black dotted line there. We've just got a fitting line there with the blue. On the right-hand side, you've got your residuals, basically is your predicted minus your chloride mass balance recharge, to see how much error you've got in those predicted versus your input data. So as you can see, the color here is showing you how the density of those points. So although we've got a big scatter, a big cloud of data, there are, points, most of the points are very close to that one-to-one line. The other thing to note here is that we do have underestimation of recharge, and that is basically all the negative values in the y-axis here. So you can see that your recharge, as it gets higher, we tend to underestimate recharge, and that's sort of that drop off as well. We're looking at there. But looking into that, majority of those errors are less than 30%. And most predictions are close to the actual recharge value. One other thing is that this validation, it's an external validation, so you're not using the same data that's been trained, you've used to train the model. So that helps us understand whether, when we do put new data into it, how good is it with predicting with new data. So I think it will be quite good at that. Another thing that you can grab out of the random forest is the feature importance plot. Basically, the y-axis here shows us how good each of these variables, which are shown on the x-axis here, at separating out that data. Basically, separate that data beforehand. And we can see that climate-related variables, which are all the blue ones here, they're the most important ones for some reason. Next, we've got vegetation is quite important, followed by surface processes or hydrogeological processes, and then soil or geomorphological sort of variables. Now that's, I think, pretty self-explanatory, because precipitation is the source of recharge, so you would expect that to be a quite important thing. You would also expect when that rainfall, occurs is quite important as well. Obviously, up in the tropics, it's quite seasonal, so that does play a part. Evapotranspiration as well, because that's how much water is removed from the rainfall after it's landed. So that does, control how much recharge gets into the ground. And vegetation, obviously, that's maybe also influenced by climate, because that they're the ones that are removing water out from the ground, from the soil. Now, in global studies, climate is quite commonly found as an important control, along with precipitation, aridity, rainfall seasonality. It's been shown. Some other studies have also found vegetation and soils to be strong predictors of recharge, in addition to climate. So I think our results here are quite in line with other studies across the world. So this is sort of our final map of recharge. I'll sort of show you a few different points on the map. So firstly, the wettest place in Australia, as many of you probably know, in Tully, in far north Queensland. where rainfall is more than 3,000 mils per year. We've got recharge in our median sort of value as 621 mils per year. But that there is an uncertainty there. And basically, by looking at the 5th percentile and the 95th percentile, we also have a range of potential possible recharge values going from 390 to 1,700 as well. So there is variability, and that's just the nature of the modelling. The driest area, though, in Australia is Coober in South Australia, with rainfall of less than 150 mils per year, and recharge that's well less than 1 mil per year. So, and the possible range of that is really low. And we also know that the variability in this model recharge is highest in the arid zone, so which is, you know, covers most of Australia. 80% of the Australian continent is in the arid zone, and that's also where we have the least data as well, in the arid zone. So it kind of makes sense where we have the most uncertainty and the widest uncertainty, and that uncertainty, unfortunately, can be spanning 4 orders of magnitude. But if you think about it that way, it's also very low numbers. So it could be 0.0001 to 1 mil, and that's sort of the range of it. But, you know, we could just lump that into less than 1 mil, and, you know, it could just make sense. We've also generated a recharge over precipitation map. So that's just that ratio of recharge divided by precipitation. And I think this will be quite important for a lot of people, hydrogeologists that do modelling. And the scale here is from 0.01, which is basically 1%, to 100%. Same as before, same as the recharge map. We've also got the most variability in 4 orders of magnitude in the arid zone as well. So how do our estimates compare to other studies that have been done around the world? So comparing the mean recharge, our point estimates, so not our recharge map, but our point estimates from previously, were 4 times lower than some of the other studies out there. In particular, the CSIRO studies that were done more than 10 years ago. I think we have a lot more data points than they did, and coverage of a lot more arid areas, which would be more representative of what you'd expect in Australia. Although a lot of the areas are still not covered by us. But our estimates were a lot lower than some of the other studies. And past studies have also utilized older data sets, especially the chloride deposition maps, which have been updated since. And also older approaches. So they weren't necessarily utilizing stochastic approaches where where we're doing things 1,000 times and then getting the percentiles there. They've also potentially used the mixture of recharge estimation approaches. So they use water table fluctuation that may have given them a much higher answer, and they're mixing that with chloride mass balance, which tends to give you a lot lower numbers. And different timescales as well that they look into. And it's difficult to compare when data is also not made available in some of the studies that are in the literature. So we've provided our data so that potentially other people, other studies later on can also be using our data to compare against their studies. And just before I conclude, yes, be aware that this isn't sort of the best recharge estimates that we have out there. You can definitely see there are heaps of gaps in Western Australia, and that's just that's just the way it is. That's obviously causing a lot of large uncertainty. There are, definitely need for more monitoring and sampling to fill those data gaps. I'm sure a lot of the agencies, CSIRO, Geoscience Australia, they're doing a lot of that. But there are lots of data out there that's obviously consultants know, mining companies and industries will have that data, but it's private, it's confidential data. So potentially being able to share that data amongst us would be really beneficial to fill those data gaps. So in conclusion, we've taken a bit of a data-driven approach to estimating recharge. We've also taken that single recharge estimation approach where we're not mixing different techniques that could give us a lot of variability. We've covered relatively large amounts of space across Australia as well. And we've generated estimates that are relatively lower compared to other studies. And we believe that they're a little bit more accurate just because of the more up-to-date techniques, data sets, etc. We need to be mindful of using different estimation techniques, as I mentioned, and also the uncertainties in the model. But I believe that this map will be a good starting point, especially where we don't have much data. So if you have a new study or a new site, you can definitely go into this map. We've provided the Python codes to be able to use it for your own studies if you like. The maps are out there as a TIFF or a text file, and all the data sets as well. The workings out basically are also there if you want to reproduce our study. But yeah, you can use the Python codes to basically get your own chloride points if you like, or you can extract it from the chloride, the recharge maps as well. And yeah, let me know if, for those people who don't use Python or coding, if you do prefer Excel. My supervisor Dylan has produced a Excel version of this, of the CM Bear basically. So he's still working on it, but yeah, do let us know if that is something that would be useful for you or your company, and we could make that available and share it as well. So yeah, thanks for letting me talk, and my contact details are here. Feel free to contact me if you have any questions, or have a chat with me later on. Thank you.
Thanks a lot, Steven. Can everyone hear me?
Yep. Yes.
Yep.
Coming loud and
Cool.
clear.
Thank you. I think Nick might be busy right now because, well, you could say that he was keeping his hands busy. But thanks a lot for the presentation. It was really, really clear, really well presented, and really valuable for us. Do we have any questions? Let's say questions online first, and maybe in the room after, if we have any. Do we have any questions online? Melissa, go for it. You can.
I don't know if they can switch off. Let me see if I can allow Mike. Okay, Melissa, there you go.
Hey, thank you. That was a fantastic presentation. Just going back to, I just came in at the start of the presentation and looking at what was either potential gross or net recharge. I'm assuming that this would be representative of potential recharge. Would that be correct?
From my understanding, yeah, chloride mass balance typically gives you a net recharge because it's the chloride in the groundwater that's come through, leaks through the soil column, and it's also after any potential vegetation and trees could have pulled up the water and changed the concentrations in the water. So from my understanding, it's net recharge.
Okay, all right, that's great. I noticed, did you make any comparisons with some example studies? Like, for example, for the Peter Cook's work, it's 1998 in the Howard River, and I guess the potential recharge was about 200, but net recharge was about 20 mils, and how that compares with I was just looking at how it compared with like a tropical sort of setting. So it seems quite high compared to, well, for the Darwin area anyway, just from my experience.
Yeah, we haven't necessarily compared it to that particular study. We did compare, the mean, I guess, the mean of all those points to some other studies, but that was because, we didn't have a lot of the other data sets to compare with. We could definitely have a look into that and check that out. Is that Peter Cook study in the tropics? Is that where it's located as well? Or?
Yeah, that's right. So Darwin, the Darwin, like Howard region, and they did look at evapotranspiration and specific, tree water take, but it ended up being about 20 mil as net, 200 as potential, for a indicative like rainfall of about 1,700 a year. And they did use a number of methods there, but this is a fantastic data set, and I'm concerned if I know you're saying it's sort of it looks lower than other methods, but I think it needs to be used with caution to make sure that it's not an overestimation in some places, and so that it would be used to, allow for over extraction in some cases. So, but I think it's great. I think it's a fantastic tool set.
Yeah, thank you. As I mentioned, it is user beware. Use caution when you're looking at these data sets. Interesting about how you say the net and the potential are quite different, and of course it's going to be to do with the assumptions and the different estimation techniques. And I guess the uncertainty bands will be interesting to see and use as a bit of a comparison against some of those studies, because that sort of encompasses the entire possible range of recharge values you might get in a particular year. So that's, I think, where you might be able to use that as a start. You could sort of try and vary it, and especially in modeling, you could try and vary it across that range of recharge estimates.
Yep, great, thank you.
Thanks.
Ian has a question. Let's
I've enabled the mics for everyone, so you should be able to just come off the microphone or off mute.
Thanks, Nick. Can you disable the mic, Ian, or otherwise you can type your question in the chat window. Well, it's not coming through, so yes, go for it, Ian.
Yeah, hi. Thank you for a great presentation. Look, just asking the question, you were looking at wells to a depth of 150 meters, is that right?
Yes, that's right.
Okay, yeah. I guess, like previously I'd done a little bit of chloride mass balance work, and I guess I was told to use much shallower wells, use the first meter or so of the water table for CMB methodology. I'm just sort of, wondering how you came up with 150 meters worth of aquifer, because there's sort of, there's quite a potential for mixing and other processes going on.
Yeah, thanks, Ian. That's a good question, and very good point as well. We came up with that number following a few studies by CSIRO. They've done similar studies, and the methodology basically is coming from them. But I do agree that having 150 meters may be a bit too high. And the point that you make that, typically you would want to sample chloride from just below the water table. That would be the ideal place. But yeah, for a study like this, where we're looking at huge amounts of data and trying to generate a map that obviously has its limitations, that's sort of the threshold that we've taken. Would be worth exploring different thresholds as well. But yeah, we've chosen that one, and so yeah, again, user beware.
Yeah, no, thanks. I remember the study I worked on. We had extremely patient drillers, fortunately, but we were putting very short and shallow screens in. But that was government work. But anyway, no, I appreciate you've got to work within the data limitations. But thank you.
Thank you.
I have 2 questions myself. The first one, thanks a lot again for for giving this to us. I haven't had a chance to check the data set, but I'm considering using it for projects, any future projects, to compare. I'm a groundwater modeler, so to compare how much recharge we put in groundwater models. And one thing that we frequently do in project scale groundwater models is assign different recharge coefficients to the different geological units that we have, or hydrostratigraphic units, if you want to call them that way. And if we grab the dataset, the interpolated dataset, would it kind of blend together most of the units and give us more a regional estimate, or does the resolution allow us, or would it allow us to give us bounds down to that scale of the different geological units that we find for studies?
Thanks, Juan. Yeah, that's a great question. I'm glad you mentioned that as well. And I think it probably wasn't very clear that it is a 0.05 degree, when you're thinking about latitude and longitude, 0.05 equates to about 5 kilometers. So it is more of a, in between local and regional scale. You're getting these grids, right, of recharge in our map that is 5K by 5K. So yes, that will be, if your site's smaller than that, then you're going to have the same recharge rate for your site if it's less than 5K, if that makes sense.
That answers the question.
Yeah, it's more of a good, gives you a range for that area, so that you can sort of explore and work out a better estimate for that. You might be better off looking at if there's any chloride or any recharge points from our recharge point map that are close by, and have a look at that as well. Because obviously there might be a few points within that same pixel, but it gives you sort of an average of that area. So it's worth looking at both of those data sets, the point data set as well as the recharge map.
Thanks a lot. And question number 2 is related to the machine learning side of it. I know how hard it is, and how it's you can go down the rabbit hole of machine learning and choosing what classification method to use, and there's so many, and a few of them might look like they work well. What was that journey like for you? Like choosing, did you try different classification methods and choose one, or did you kind of choose how I look at just 2 and went with the best one, or just received advice from someone else? Or what was it like for you to find a good machine learning method?
Yeah, I've forgotten how I came across random forest, but I think maybe my supervisor suggested it. And yeah, it had to be regression, and it was freely available. I was just learning Python as well, and it was helping me out with the data side of things. And I found out there was a SciPy toolkit which has that in there built in. So I downloaded the library. As you said, you can go down the rabbit hole. It can take a long time to try and figure out what's happening, especially because there's so many of those hyperparameters. How many, how long do you want your tree to be? How many samples do you want in each of them, and how many variables? And so there are tools out there. There are built-in tools that can help you. One called grid search, I think, which can help you optimize each of those hyperparameters and give you a good starting point to go with, and then you can sort of start looking at changing variables and things like that. But use ChatGPT if you can. Use whatever forums and things. There's a lot of stuff out there to help you do that. But yeah, as you can see from my recharge map, it is has a lot of uncertainty around it as well. It gives you a best guess, but that guess may not be the best guess. It could be somewhere in between. Yeah. Hopefully that
and do we have any more questions in the room or online? It looks like that's it. So Steven, I just wanted to say, well, for people who don't know, Steven is a representative of IAH in Townsville. So lucky you guys in Townsville for having him, such as my person, a nice person, helping on that side as well. And it felt like a really clear, really well presented piece of work, and I kind of appreciate many things behind what you presented. Like you chose color scales that are very modern color scales, and not many people use them yet. You published your work in an open journal rather than a paywall journal, so anyone can access it. And you made the effort of publishing all your data, as you said, so that anyone can reuse it and make everything open. And I feel that that's a really modern, transparent, and a commendable way of doing science. So thanks a lot for what you did, Steven. Yeah. Thank you. Thanks everyone, and see you next time.
See you.
Thank you. Fantastic.